So the next example I would like to do is in your textbook. It's question number 1736. This is on page 713. So in this particular problem, what we have is a reaction, a decomposition reaction of 2NOBr producing 2 NOs and bromine gas. We are told that the conditions are 100 degrees Celsius for temperature. And we're told that the Kp for this reaction is 60.6. Now, I don't want this to look unfamiliar to you. Just see that Kp and Kc are the same. The difference is that in the problem at hand, 17.36, we are dealing with gases with pressure instead of concentration and molarity. Each one of these starts with 0.10 atms pressure. And so in that case, we would deal with not an equilibrium constant in terms of concentration, but an equilibrium constant in terms of pressure. So how do we know it's at equilibrium? Well, we know it's at equilibrium because there is a double arrow. So that suggests the reaction can go both ways. The question asks, are we at equilibrium, and if not, in which direction does the reaction go? So question number 1 is equilibrium. And question number 2 is, if not, which way? Are we going to go right or left? Are the reactants favored or are the products favored? Well, I bet you could guess. If we were to then take a look at this, we would say, oh, we need to find the reaction quotient. Just like we did for the reaction of HI, we found QC. This time we're going to find QP. So let's start by writing an expression for QP. QP is equal to the concentration of the products over the concentration of the reactants. Remember, that's always the way we do equilibrium, products over reactants, okay? So this is going to be the concentration of NO, first product, squared, because it has a 2 for coefficient, times the concentration of bromine, that's just single, so it's to the first power, divided by the concentration of NOBr squared, because again the coefficient is 2. We're not at equilibrium necessarily. We don't know. What they tell us is that you're given 0.1 atmospheres of each. So that's the pressures of those. So you might say, okay, all right, we're looking at the pressure of NO squared times the pressure of bromine. Again, not to confuse you, but concentrations we've talked about before are moles per liter. Here you've got atmospheres worth of pressure. So really the concept is the same, just treat it the same. Divided by the partial pressure of NOBr squared. We know the values. We know that NO is 0.1 atmosphere because that's what we started with. We know Br is 0.1 atmosphere, and we know NABr is 0.1 atmosphere, and all that's going to be squared. Well, look, this is nice because 0.1 squared over 0.1 squared. That gives us 0.1, doesn't it? I don't even need my calculator for this one because those would just cancel. And I get a QP of 0.10. Okay, now what you do next is you say, all right, make a comparison of Kp and QP. We compare the reaction quotient in terms of pressure, in terms of the equilibrium constant in terms of pressure. We see that the equilibrium pressure constant is 60.6. We see that our reaction quotient is 0.1. And we know that QP is less than QP. So what does that tell us? Well, that tells us then that the reaction is going to proceed to the right. So that is, the products are going to be favored over the reactants. In other words, the product should increase in concentration and the reactant should decrease in concentration. That's number 1736.